How does the measurement problem impact wave-particle duality? Imagine watching a tiny particle like an electron or a photon move through space. Sometimes it acts like a wave, spreading out and creating interference patterns. Other times, it behaves like a solid particle, hitting a specific spot. This strange behavior is called wave-particle duality. But there is a puzzle at the heart of this, the measurement problem. It makes us wonder how and why these particles switch between wave and particle states. In quantum mechanics, particles are described by a wave function. This wave function tells us the probability of finding a particle in different places or states. Before we measure anything, the wave function exists in a superposition, meaning it combines many possibilities at once. It acts like a wave spreading out over space, which explains phenomena like interference and diffraction. But when we measure the particle, something strange happens. The wave function suddenly collapses, and the particle appears at a specific location. The problem is that the wave function evolves smoothly and predictably according to the Schrödinger equation, which is a fundamental rule of quantum mechanics. This evolution is deterministic, meaning it follows strict mathematical laws. But the collapse of the wave function during measurement is sudden and unpredictable. It is not explained by the Schrödinger equation itself, creating a big gap in our understanding. This gap impacts wave-particle duality because the wave-like behavior is only visible when no measurement is made. When we do measure the particle, the wave function collapses, and the particle-like behavior appears. For example, in the famous double-slit experiment, if we do not look at which slit the electron passes through, we see an interference pattern that shows wave behavior. But if we try to find out which slit the electron goes through, the pattern disappears, and the electron acts like a particle. So, the measurement problem is central to understanding why quantum objects sometimes behave like waves and other times like particles. It also influences how we develop quantum technologies. Quantum computers and sensors relying on maintaining superposition states, which are wave-like, until a measurement is made. But the challenge is controlling when and how the wave function collapses. In summary, the measurement problem affects wave-particle duality because it governs the transition from a spread-out wave to a localized particle. This transition is not fully explained by current theories, making it one of the biggest questions in quantum mechanics. It shapes how we interpret quantum phenomena and develop new technologies based on quantum principles.